Now let us understand what is Gauss theorem in electrostatics. Gauss theorem, it is a mathematical theorem to find the electric field due to certain symmetric charge distributions. So let us first see the statement. For remembering the statement, we write the mathematical form of the Gauss theorem first. I have written here phi. Phi is the electric flux. What is phi? Phi is the electric flux. First we had written d phi, but if you take integration, then phi is equal to integration of E dot ds is equal to q upon epsilon naught. Now this integration we have to take over the closed surface. For that we write this round symbol over the integration sign. Now the statement of Gauss theorem is the total electric flux passing through any closed surface is given by the surface integral. So surface integral of electric field. The surface integral of electric field over the closed surface, and it is equal to 1 upon epsilon naught times the charge enclosed. 1 upon epsilon naught times means it becomes q upon epsilon naught. So if I repeat, then Gauss theorem is stated as the total electric flux passing through any closed surface enclosing a charge is given by 1 upon epsilon naught times the charge enclosed by the surface. So this is the Gauss theorem. Now we have to study certain applications of Gauss theorem. That is where we can use this to find the electric field. So the applications are very important from our exam point of view. So the first application is to find the electric field due to a linear charge distribution, that is due to an infinitely long straight conductor. So let us study the application of Gauss theorem for finding electric field due to a straight long conductor. Now I have to consider a straight conductor like this. This is carrying a charge. Let me consider the whole conductor having the positive charge. Let that total charge be Q. Let L be the length of this conductor. Now I have to find the electric field at a certain point P away from that conductor. Let this point be at a distance R from the conductor. Now at this point I am interested in finding the electric field. Now using the Gauss theorem, I have to consider the surface integral over a closed surface. Now there is no closed surface here. So what we have to do is we have to draw one convenient surface called Gaussian surface, which will enclose this charge. Now the convenient surface for this is like this. What is the surface? This surface you can see, it is a cylinder which is enclosing, and we have considered this linear charge or a straight conductor as the axis of this cylinder, and this we are calling as a Gaussian surface. Gaussian surface. So what is a Gaussian surface? It is a imaginary surface which we draw, which will enclose that charge, and we draw that through the point at which we are finding the electric field. So here let me take this point P here. So that point, through this point the Gaussian surface is passing. Now to apply the Gauss theorem, I have to take a small ds. Now that ds is the area vector. This area vector is having the direction perpendicular to the surface. Also the electric field lines passing through this are also along the same direction, that is perpendicular to the surface. We draw always electric lines perpendicular to the surface. Now you can see both electric field and ds, that is area vector at this point, both are having the same direction. So the angle between them is 0. So when I apply Gauss theorem, I get E into ds into cos 0 because the angle between E and ds is 0 is equal to q upon epsilon naught by Gauss theorem. By Gauss theorem I can write like this. So now this is E, cos 0 is 1, so I can write integral of ds is equal to q upon epsilon naught. Now what is the integration of this surface? Integration of this surface is the, I write closed integral. Now here this will have only the curved surface area of the cylinder. There is no flux in this area direction or this direction. This is because we take the electric field lines perpendicular to the line. So if I have this, lines of forces are in this direction and this direction. There is no electric field line in the same direction as the conductor. So I am taking only the area of the curved surface of the cylinder. So what is the formula? It is 2 pi r into L. You know the formula for curved surface of cylinder? 2 pi RL. So 2 pi RL is written here. So is equal to q upon epsilon naught. Now I want to get the expression for E. So I will keep E on the left side and I will get q upon 2 pi r L into epsilon naught. Okay, this is the expression. Now Q by L we have studied linear charge density. Just before this topic we have studied Q by L is called charge per unit length. You can keep the expression like this or you can write this final expression as Q upon L to be written as lambda upon 2 pi r into epsilon naught. So this is our formula for electric field due to a straight long conductor. So electric field due to a straight long conductor is inversely proportional to the distance from the conductor. As you go very far away, the electric field will go on decreasing. Now we go on to the second application, that is due to a spherical shell. What is a spherical shell? Spherical shell is a hollow sphere, just like a ball. You have only the outer surface. Inside it is hollow. So it is called as a spherical shell. And it is having a certain charge on its surface. Okay. So the question is, derive an expression for electric field due to a charged spherical shell. And the point is outside the sphere. Or it can be on the sphere. And it can be inside the sphere. So we are going to see these three cases wherein we have to use the Gauss theorem and get an expression for electric field at a point outside a charged spherical shell, on the charged spherical shell and inside the charged spherical shell. So let me consider a charged spherical shell of radius r. So if I consider a charged spherical shell, say like this, let this have a radius r. Now capital R is the radius. Everywhere it is having a charge. Plus Q charge is distributed. It is a continuous charge distribution. So we have to take that continuous charge distribution as surface charge distribution or sigma. Now a point is outside. First is outside the shell. Outside the shell. Point P is here, which is outside. P bahar hai. Now it is at a distance r from the center of the sphere. It is at a distance r. Now again you have to remember, whenever we have to find the electric field using the Gauss theorem, we have to consider a closed surface because it is applicable to the closed surface. Surface integral over the closed surface. So we draw one Gaussian surface. There is no closed surface. We draw imaginary surface through P. Now this surface should be a symmetric surface. For all the points it should be applicable and it should be a convenient surface. So it is naturally a sphere. Gaussian surface will be a sphere passing through this point P. Now we consider a small area. As you know, area vector we have to take. So that area vector will have ds direction here. and electric field also in the same direction. Both are along the same direction, so this becomes convenient if the surface is very symmetric. Now E dot ds, apply the Gauss theorem again. So our formula becomes E into integral of ds. This is again because both are in the same direction. I had explained you that E dot ds is E ds cos 0. So 0 value 1. So therefore E ds is written like this, is equal to q upon epsilon naught. Now ds, the integral of this over the closed surface. What is the integration over the sphere? It is the area of the sphere. What is the area of the sphere? It is equal to 4 pi r square. Now here, this is the Gaussian surface. This is the Gaussian surface. So area of the Gaussian surface you have to take. So that is equal to E into 4 pi r square is equal to q upon epsilon naught. Now I can write E is equal to this. If I write here, I get 1 upon 4 pi epsilon naught q upon r square. So this is formula for electric field due to a charged spherical shell. Now this formula you must be remembering that this we have studied for a single charge, electric field due to single charge. So this sphere is behaving as if the whole charge is concentrated at the center, that is O. So this is the formula for electric field at a point outside the shell, Now it can be written in another form by taking sigma. What is this sigma? Q by A. A is here, this area on which the charge is distributed. So we have to take 4 pi capital R square. Why 4 pi capital R square and not small r square? Because we are taking the surface charge density of the sphere. So charge is distributed on this sphere. So we have to take capital R square here. So the value of Q becomes, I can substitute here. So it becomes E is equal to 1 upon 4 pi epsilon naught into Q is equal to 4 pi capital R square into sigma upon small r square. So 4 pi will get cancelled. So I get the formula for electric field as here r square sigma upon epsilon naught r square. So this is our expression for electric field outside the spherical shell. I hope it is clear to you. Only you have to apply this last term is something new for you. This is sigma, that is surface charge density, continuous charge distribution, Q upon 4 pi r square. So Q is substituted as 4 pi r square sigma. From this expression, Q is substituted as 4 pi r square into sigma in this expression. So in this way we get the formula for electric field due to a spherical shell. Now on the sphere, the second point is we consider the point here on the sphere. So if you consider it on the sphere, what we can do is we can simply write small r is equal to capital R. So in this formula which we have already derived, we can write electric field is equal to r square sigma upon epsilon naught r square. I have taken both as r square because here the point, the second is on the sphere. So on the sphere if I want, then I will write small r is equal to capital R. So if I write it in this formula, small r equal to capital R, I will get the formula E is equal to sigma upon epsilon naught. This is the formula for on the sphere. So on the sphere, this is outside the sphere. Outside the sphere. And the third point which remains is inside the sphere. Now I go inside the sphere here, somewhere here or here. Wherever I want to go, I have to consider a Gaussian surface. So if I consider a Gaussian surface inside the sphere, that is the third case, inside the sphere. So you have to remember very important thing here, that inside the sphere there is no charge which is existing. In a hollow sphere, the whole charge exists outside the sphere only, on the sphere. So inside the sphere there is no charge. Therefore, E ds is equal to Q upon epsilon naught. Q is 0. So electric field inside a sphere is always 0. Whenever the spherical shell is asked and a point is asked inside the sphere, it is called as electric field inside the sphere is always 0 because no charge exists inside the spherical shell. This is called as the cavity effect, that is, or shielding, wherein the whole charge lies on the surface. If there is a hollow conductor, then inside that the electric field will not exist or it will be 0. So this we have studied the second application. First we have studied due to a straight conductor. Then second we have studied due to a charged spherical shell. And the third one is due to a plate. So let us see the third application, that is due to a plane sheet. Now due to a plane sheet, we draw one plane sheet like this. It is having a certain charge Q on the sheet. Let us find the electric field at point P due to a charged plane sheet. Due to this charged plane sheet, certain electric field will be produced and we are finding the electric field at point P. So the first step is, for Gauss theorem, we have to consider the Gaussian surface. Now think of the Gaussian surface passing through this point P, and it should the plate is kept like this. So the lines of forces are passing through this point. So for that, the convenient surface will be like this, a cylinder, and electric lines are passing through the cap of the cylinder. Okay, the caps of these circular faces of the cylinder, the electric field lines are passing, and the area vector is also along the same direction. ds is the area vector. So by applying Gauss theorem, we get E ds is equal to Q upon epsilon naught. E and ds are in the same line, so again ds is equal to Q upon epsilon naught. E, now ds. For convenience, let us take the area as A. This area is also A. So on both the sides the lines are passing. So the total area becomes 2A is equal to Q upon epsilon naught. So electric field becomes Q upon 2A epsilon naught. So I hope you have followed this. Q by A is written as sigma. So our formula becomes E is equal to sigma upon 2 epsilon naught. Q by A I have written as sigma, charge per unit area. So this is our formula. E is equal to sigma upon 2 epsilon naught. This is the formula for electric field due to a plane charged sheet, and sigma is the surface charge density. One application of this, or one case for this, is if the plane sheet is thick or a thick sheet, the charge will be distributed on both the surfaces. If this is a sheet, here also and here also. So I have to take that, in that case, for a thick sheet, I have to take the charge as 2 times the charge. Must take the sigma as twice. So electric field becomes 2 sigma upon 2 epsilon naught. So I get the formula for thick sheet as E is equal to sigma upon epsilon naught. So for a thick sheet, the formula is electric field is equal to sigma upon epsilon naught. So we have studied these 3 applications today of the Gauss theorem: the plane sheet, the straight conductor, and the third one is a hollow spherical shell. So I hope you have understood it. Thank you.